So defects, what are they good for? Defects are, first of all, they're important things to study if you want to describe real-world physical systems. For example, they could be used to model quantum impurities, boundaries of finite-sized physical systems, or domain walls separating differently ordered regimes. On the other hand, defects are also essential if you would like to have a better understanding of the structure of the quantum field series, in particular the non-perturbative behavior of the quantum field series. So for that purpose, people often study line defects, surface defects, domain walls, or boundary conditions, etc. In the QFT language, there are various different ways to incorporate defects. The first kind of way is to describe the so-called order type defect, which is included in the path integral by insertions of exponentiated integrals of defect density over the defect word volume. Famous example are Wilson lines in the gauge theory. The second type is a disorder type. And we introduce such disorder type defects by specifying boundary conditions along the defect word volume in the path integral. Famous examples include duped lines in gauge series and also monodromy defects, which are certain codimension 2 objects. And in general, one could have mixed type, so which literally means a superimposition of the order and disorder types. For example, generically in gauge series, you will have Wilson duped lines. So the ultimate goal, of course, is to study defects in a generic quantum field series and in particular non-supersymmetric quantum field series. And unfortunately, that's not what I'm going to be mostly talk about today. So today, I will tell you some stories about defects in SUSY series. The hope is that with this actual amount of supersymmetry, it gives you some extra control for you to say something explicit or exact about the defects. And hopefully one could learn some lessons by studying defects in SUSY series and apply to non-supersymmetric series. And that's definitely something I'm interested in, and I hope to get there in the near future. Just the outlook. So today, our roughly first half or maybe half plus a quarter of the talk will be about line defects. And in particular, I will talk about line defects in a large class of 40 QFTs with 8 supercharges, the so-called 40=2 class S series. This part of the talk is based on my work with my collaborator, Andy Netsky, who is a math professor at Yale. And I will mention also a little bit of story about line defects in 3D quantum field series with 4 supercharges, the so-called 3D=2 class R theories. And this part is based on some work in progress with Davide Gaiotto, Asan Khan, and Greg Moore. In the second part of the talk, I will be describing some stories about surface defects in 40=2 series and associated exact WKB method for Schrödinger-like equations. This part of the talk is based on some of my own work and also a little bit work in progress with Samuel Jung, who is a postdoc, a fantastic postdoc at Rutgers. And I would like to say that in particular, this part about the exact WKB method could be taken out of the context of SUSY or defects. So you could view this as some sort of little trick for you to get exact solutions for Schrödinger-like ODEs and to study various quantization conditions for different spectral problems. And that doesn't have to have anything to do with SUSY or defects, and that could in potential have a broader application. In particular, I won't have time to talk about this in my talk. A group of people has applied this kind of ideas to black hole perturbation theories. And they find a way to compute, for example, quasi-normal modes in the black hole perturbation theory. And I would be very interested to talk more about that later in the talk, after the talk, as I'm also starting to look into these applications in this related areas. And I should say that in all the stories I talk about today, they always involve certain UVIR map, which takes a UV description of quantum field series with insertions of these extended defects to some infrared effective descriptions, which are in general simpler. So that's kind of the motivation that by using this kind of UVR map, you could translate a harder problem to something more tangible, more a bit simpler in the infrared effective theory. Okay, so let's start with lines. Line operators in general are important in quantum field theories. Historically famous examples are, for example, Wilson lines and Duft lines are important observables in studying physics of 4D gauge theories. More recently, these kind of ideas have been explored in a more systematic way, where people realize that line operators and their correlation functions really capture the global structure of quantum field theory. What I mean by global structure? So you could have, imagine you have two gauge theories with the same gauge Lie algebra, but with different global form of the gauge group. For example, you could have a SU2 gauge theories versus a SO3 gauge theories. And to detect the difference between these two different gauge theories, one could look at the set of allowed line operators in each theory. In that sense, line operators and correlation functions really capture global structure of quantum field theory. And more dramatically, if you take a theory and compactify it on a circle, then line operators in the parent theory directly affect local dynamics of the theory compacted on a circle. For the simple reason that writing a line along a circle will produce you a local operator in the compacted theory. As another example, if you consider line defects, which model insertions of infinitely heavy particles, and by studying the response of your Bach theory to the insertions of such line defects, you can learn something. You can learn some information about the Bach spectrum. And I will get back to this at some small comment on midway in my talk.
May I ask?
Yeah.
So here, sometimes you use two different definitions of like what global means. In your second bullet, it was really global in the sense that global structure of gauge group matter.
Yes.
And in the third bullet, it's more like to see this difference, one need to do something non-local in space-time and compactify in a circle.
Yes, yes.
So, but it's very different notion of local. Is there coincidence? Is there a simple way to understand why kind of these two are related?
Yeah. This two not necessarily related. I'm just trying to say different aspects of why people care about the line operators. And the third one, I should say, it affects the local structure. Literally, if you think of line wrapped around this compactification circle, it become a local operator in the compact theory. That's what I meant. Yeah, I agree. There's some.
But maybe the point that's related to what Sergey is asking is, so if you don't insert these lines, you need to consider topology, which is non-trivial, like the S1 quantification to see the effects of lines. But if you explicitly insert these lines, it's like creating some non-trivial topology that detects the global structure of the gauge groups. So there are two different ways to detect this. You can either consider non-trivial manifold, or you can consider explicit insertion.
That's welcome. And right. So the last point is relatively more recent point of view. Namely, there has been a series of work to study the so-called topological line defects, and in general, they generate some sort of potentially non-invertible generalized symmetries, and just like ordinary symmetries, such generalized symmetries could have dynamical implications. So this is also a new area regarding lines, and there has been more and more work appearing in this field. Okay, so let me start with my first story, namely the line defects in 4D equals SUSY series and the 4D quantum field series with H supercharges. Concretely, we take a 4D equals SUSY series and we insert a line defect extending along time direction, preserving some supercharges, and say sitting at the origin of the spatial R3. Now, notable example, you could think of it as a supersymmetrized version of the general Wilson-Duft lines in gauge theories. However, that could also be generalizations. If you take a generic 4D equals SUSY series, such lines could be difficult to study. However, if you just take some abelian gauge theories, such objects are very explicit and they could explicitly describe it. Namely, in a Billing gauge series, you could literally think of these lines as word lines of heavy BPS diodes with certain electromagnetic charge gamma. In other words, they are labeled by electromagnetic charge gamma and also some parameter, say star parameter, labeling which supercharges does this line preserve. And one could explicitly write down such an insertion of line defect in the following way. For example, if you just consider 40 equals to U1 theory, you pick an electromagnetic duality frame such that gamma is purely electric, then the insertion of such line defects is explicitly written in terms of this exponential of the integral along time direction. Where here, A is a gauge field in the U1 theory. Phi is a complex scalar, which is related to A by this n equals 2 supersymmetry. And then you can see that by varying this say star parameter, you get a choice of which subset of supercharges does this line defects preserve. So it's some explicit thing. Now, I told you that take a generic 40 equals 2 series, it could be hard to study those line defects. On the other hand, if you take up Billing theory, they're more explicit to describe. So one could ask whether there's a way to exploit this fact to use this Billing gauge series to describe this more complicated line defects in 40 equals 2 series. And that brings us to this concept of the UVIR map. So 40 equals 2 series, just like many quantum field series with extended supersymmetry, it has continuous space of vacuum, in particular subspace of vacuum, the so-called Coulomb branch. Where the takeaway point for the Coulomb branch is that at a generic point on the Coulomb branch, one gets an effective field theory, which is some Billing gauge series, so a bunch of U1s. So what one could do is you start with the supersymmetric line defects in the UV, deform the buck onto the Coulomb branch, and then follow the line defects into the infrared. What you would find is instead of a single line defects in the infrared effective theory, you get a superposition of line defects in this effective Billing theory. And this kind of description could be summarized as the following UVIR map for line defects. So namely, I start with this UV line defects on the left, deform the back onto Coulomb branch, and then I'll get a sum or superposition of infrared line defects, which I represent is in terms of this symbol X gamma here. And each X gamma is an infrared Wilson-Dupf line, or you could think of it as word line or some heavy diodes with electromagnetic charge gamma. And there are some integer coefficients in front of each term in this decomposition. This such integer could be interpreted as some index counting the ground states of the back defect system. So to properly define this thing, we look at this object in this right of whatever color that is this box. So the so-called defect Hilbert space. So recall that the defect is extending along time direction. So it modifies the Hilbert space on R3 at a point. So we take this defect Hilbert space, and moreover, going to the Coulomb branch means we fix the vacuum at infinity to correspond to some point on the Coulomb branch. After you do that, such defect Hilbert space admits a decomposition into different superselection sectors, labeled by gamma, which is electromagnetic charge. And within each superselection sector, I could define an index counting the ground states within that sector. So that gives you these integers in front of this decomposition. One can actually do a better counting. One can do refined counting, refined by the spin of the ground states. Essentially because this line defect is inserted at a point in R3, so it preserves the SO3 rotation symmetry and also preserves some R symmetry. So you could use these symmetries to define a refined index counting these ground states within each superselection sector with their spin data. So this spin refinement in general will be some long polynomial in Q. However, after you set Q goes to 1, you get those integers in this decomposition.
So, yes. So when you talk about decomposition, so first of all, is it general like finite sum, or there is the sum of a gamma?
The sum will be finite in general, generically.
What's the reason for this to be finite?
Sorry.
What's the reason for this to be defined? More generally, is there some natural basis in the states? Because the way you describe it so far, it looks like defect is a very general thing. They can really write something completely general along the world line.
Yeah.
Now, for local operators, we kind of, well, first of all, in the gold logic, usually we kind of only care about relevant ones, right? So in some sense, there's some UV operator and if it's effect in IR, we approximate by some of like relevant operators or marginal operators present in IR theory. So I guess there's some similar notion for these defects, right? So in principle, probably for generic defect, exact expression would have some infinite sum here. But when you go to low energy in IR theory, somehow there is some of them which are relevant in some sense.
Yeah, so first of all, the sum, I'm only talking about this effective infrared theory. So
Right.
in a sense, I guess it could be in general, you would have an infinite sum. And then once you go to infrared, you have a finite, you keep a finite sum of the lines. But I mean, I don't really have control over what exactly happened, what lines get forgotten or something.
Sorry, the set of gamma is infinite.
Yeah, the reference set of gamma, is it infinite?
But you're saying the coefficients could be zero. Is that what you're saying? I mean,
Yeah, I'm saying the terms in the sum is a finite.
No, my question was more about the number of terms, like the set of gamma.
Gamma is-
Oh, the set of gamma is infinite, but the term in the actual sum is finite. Sorry, I misunderstood. I thought you were saying there should be an infinite sum of lines, but no, that's not the case.
I think it's essentially what you said.
Right, but also
okay.
the question about this X gamma, because in principle, kind of on the word line of a defect,
Yes.
I can write like many
That's right.
local operators. And
Yes.
somehow here one drops
That's
irrelevant
right.
ones.
That's what this index is doing. Index is only counting those ones that are, in a sense, those are relevant, that are important in IR, and dropping other things. That
Right, so this is really analog of like relevant and marginal.
But there's,
local
but
operators.
yeah, but you have to be careful about that notion.
Right, yeah. But is there a precise way to say?
In the sense that these are lines that do not flow further in the Soviet engaged theory. So this S gamma has the explicit definition that I think Fei showed you.
Yes.
If you do something else, that's going to flow to, for example, a trivial line.
So in that sense, these are all the conformal.
Well, they're not quite conformal because
This one
the effective theory is a really
is a
engaged
frame,
theory.
so-
So the bulk theory is
That's,
not conformal.
Right.
It's some free theory.
Thanks. Yes.
Maybe a related question, but in the UV, you said these were like mixed, Tupt and
In
Wilson
general,
lines.
could be, yeah.
So they include, as you said, like boundary data,
What boundary
Uh,
data?
like to define the Tupt line.
Yeah, if you want to define a mixed type, yes, it's a superposition of the Wilson line and the specification of boundary condition. That's the most general case.
Okay, but in the UV, you only have these are Wilson lines. It looks like so.
No, the infrared.
I'm sorry, infrared. Sorry, in the
Yeah.
infrared, they're Wilson lines. So what? I'm just kind of curious what happens.
There's
at
also
boundary.
magnetically charged lines in the infrared. Actually, I was going to get to this.
Okay.
So these are some just generic dion operators.
Exactly, yes. Generic diodes, not necessarily pure electric charge. So yeah, thanks for the questions. They're great. So actually that brings me to this simple example I would like to show. So namely, if you consider this n equals to SU2 super Young Mills, so SU2 gauge theory, but you super symmetrize it so that it's n equals to. I go to a region far out of the Coulomb branch in the wake coupling region where the SU2 gauge group is broken to U1. And then suppose I started with this fundamental Wilson line, the fundamental representation of SU2. And I wonder what this line becomes in the infrared in this wake coupling region. And I will discover 3 different lines. And the first 2 lines in blue, is sort of consistent with the semi-classical analysis. Namely, if you start with the fundamental representation, you would expect to find a sum of purely electrically charged lines corresponding to the weights of the fundamental representation. However, there's also, for example, this purely magnetically charged line. So this term is not easy to describe from this kind of semi-classical description. One way to possibly understood this term is sort of like you could think of it as a bound state between one of this the electrically charged line, this -1 charge line with some back BPS particle. So I won't be able to get to details of that kind, but I want to emphasize that exactly these actual terms, which is you would not imagine from the same classical computation is the difficulty of figuring out this UVR map or this ground states counting in different superselection sectors. And in general, there could be different ways to do that. What I've described today is a sort of like a geometric way to figure out this kind of extension or this UVR map or this counting of these ground states weighted with spin. So that's also going to be harder. The example I gave you has trivial spin. So ground states in those superselection sectors are trivial under spin. But there are more examples I will show that they will really form some representations on the rotation.
Another question.
Yeah.
So is there some notion of positivity for this coefficient? So maybe
Yes, there is some. Although in my notes, in my where did you stick? So in my definition, I should say it's positivity minus q. So in my definition, it will be a positivity minus q if there is a multi-dimensional representation. Yeah, there is a positivity statement. Essentially, it says like for this, so the states will be charged trivially under this SU2R symmetry. And in the end, you just get this minus q expression.
Yeah, the positivity is just from you have this effective space. So it's a sum over space.
Right. So this coefficient it's counting the number of states, but the refined one also has the relevant the number of positive. Okay.
Sorry.
Yeah.
What happened? Do you remember what happens to the Wilson line edge representation?
I don't remember, but it has like maybe 3 or 4 more extra terms than this.
Can I understand that by using the fusion rule of the Wilson line?
Yes.
Okay.
You can. The fusion rules are the scale.
The fusion rules is preserved by this
Yes.
UVIR map. Okay.
Yes, but on the other hand, if you require the fusion rule is preserved, you cannot eliminate the possibility.
Sure.
Of this.
Sure.
So, but they are preserved. Yes.
But is that a useful relation to kind of bootstrap?
Yeah. In a sense, that's what we do. I will not really talk about detail what we do. What we do is like a bootstrap method by requiring this kind of fusion rules or OPs is preserved. Then we set this as constraints on bootstrap, and then we use like some huge Python program to compute this kind of thing. Okay. So I'll tell you a little bit more about this geometric way to compute such a thing. And for that, I will restrict to a subclass of 4D equals 2 series, a so-called class S series. Such series have a geometric origin. So you could find this series by compactifying some higher dimensional theory. In this case, it's going to be a 6-dimensional theory, and you'll compactify on some Riemann surface, and then modulo those details, and then you will get a 4D equals 2 series. So you could ask, how do I get line defects in 4D? I start with a 2-dimensional surface defect in 6D, and I wrap these 2 dimensions in this way. So I wrap it along the time direction and also wrap it along this little loop on the Riemann surface. So after compactifying on this internal Riemann surface, I get a line extending along time direction. So takeaway message that I would like to you to know is essentially this sentence, namely, if I think of line defects in this kind of class S series, geometrically they're represented by those little loops on Riemann surfaces. So this UVR map for going to the Coulomb branch also has a relevant related geometric description. The point on the Coulomb branch is going to be represented by an n-fold branch covering C tilde over the Riemann surface C. Where C tilde is a so-called cyber-Witten curve, it encodes the low energy effective theory data. But I draw this schematic picture for this branch covering. So of course, C is a Riemann surface, it has real dimensional too, but I'm just drawing this as a real slice. So this black line represents C, and C tilde in this case I draw is a 3-branch covering of C with 2 simple branch points, at least locally in this picture I draw. And recall that the takeaway point from last slide is that the line defects L in the UV class S series correspond to loops on the Riemann surface C. Now, similarly, the line defects in the infrared theory will also correspond to loops, and it's going to correspond to loops on L tilde upstairs on this covering C tilde. So namely, geometrically, this UVLR map for line defects, I could interpret it as an algorithm or scheme, which takes a loop downstairs on the Riemann surface and uplift to sums of loops upstairs in the covering C tilde separation curve. And classically, recall that this expansion has those integer coefficients. If you do this kind of geometric uplifting, you will be able to get those integer coefficients. However, if you want to do the refined counting, you get those Q characters, the characters under the rotation group, you need to think a little bit harder. So that brings me to another topic, which is some actual structure on the space of line defects. So recall that line defects are extending along time direction. They're inserted at a point in space. So you could consider the collision limit where you bring two line defects together. Thanks to supersymmetry, this limit is non-singular, and you get a new line, which I denote as this product notion L1 times L2. So this kind of OPE gives you an algebra structure on the space of line defects. And this algebra structure admits a quantization where the so-called skein algebras, which I will very briefly describe in the next slide. Physically, this kind of quantization could also be understood in the following sense. So recall that originally the line could be inserted at any point in the R3, in the three-dimensional space. If I turn on this so-called omega background on a R2 plane, those lines are going to be restricted. So the insertion point of the lines are going to be restricted to sit along a fixed axis in space. So such as this RH thing I draw here. Now if you consider the collision limit of the two lines insertion, the order where whether L1 approach L2 from the left versus L1 approach L2 from the right will be different because they're fixed at this axis. You cannot move it out of the axis and then move it around, switch out. So in that sense, this OPE will become non-commutative. So that's what this quantization is roughly about in the physical sense. And again, in the UV, this kind of skein algebras could be difficult to describe. In the infrared, one can describe this pretty explicitly using the so-called quantum torus algebra. So this is what I wrote here. So on the left-hand side, I have two diagonal lines with charge gamma 1, gamma 2. When I put them together, you would imagine to get a diagonal line with charge gamma 1 plus gamma 2, because the charge should be additive. However, there is also this actual contribution term. This contribution could be interpreted as follows. So on the left, you have two diagonals. There's some angular momentum stored in the electromagnetic field sourced by the two diagonals. And that contribution has to be taken care of when you go to the right-hand side, when you just have a single diagonal. So that contribution is given by this actual term, where this bracket gamma 1, gamma 2 denotes the direct Schrödinger-responsive pairing of the infrared charges. So as we said here, both in the UV and IR, I have this huge space of line defects, which has some algebra structure, which further admits some quantization in terms of skein algebra. So if I want a so-called quantum UVR map, or in other words, I want to count those ground states with spin, I would like a map from the UV skein algebra to the infrared quantum torus algebra. And moreover, I want to preserve the OPE on both sides. So that gives you pretty strong constraints on what kind of map that could be.
So may I ask
Yes.
about this slide? So here, I understood correctly, the absence of singularities that relies on BPS properties essentially.
Yes.
So if these lines are non-supersymmetric, so what is there some generalization of this whole story about the OPE? So then there will be some singularities, right?
Yeah, so here the argument the singularities will be Q exact, where Q is supercharges preserved by the line. So if you pass to the level of Q homology, then in general, yes, there will be singular terms. But here we're considering up to Q homology in a sense. That's how you get this regular algebra structure.
I think what Sergey is asking perhaps is if you consider the non-supersymmetric case,
Right.
you consider the fusion, is there some way to regularize the divergence to get a meaningful fusion product? Or that's not possible?
I don't know if that's not possible. Sounds really strong.
I'm not sure it has been studied.
Um,
In 2 dimensions, in special theories like the free boson sig-1, this has been found. But that's also thanks to special properties of two-dimensional theory.
Yeah, I think in general it's hard to
Yeah.
to
Yeah, this is very different from OPF local operators.
yes. Okay, I'll just very briefly talk about skein, but it's just some mathematical thing. But let me just maybe go back to those slides. Recall that we have this geometric picture where the UV lines correspond to loops on the internal Riemann surface, and the infrared lines correspond to loops on C tilde. For this quantized version of story, instead of like loops on a 2 manifold, I'm actually considering links on 3 manifold. Particularly in the UV, I'm considering links associated with the 3 manifold, taking the form of the Riemann surface across the real line, where you could sort of like think of this real line order, introduce an actual ordering. In the infrared, the relevant 3 manifold will be separating curve with branch covering times the real line. And the algebra structure is literally given by stacking links along this real line direction. And then we're considering the links up to some skein relations, which I will not describe, but just make a comment that you can see the left-hand side denotes these UV skein relations. It looks a little bit more complicated than the right-hand side correspond to the infrared skein relations. This is another representative that by going from UV to IR, you sort of have a roughly more simplified structure, which you could have, you could use this fact to get some statement about UV lines. Okay, so this quantum UVIR map, I'll just quickly describe what it computes. Roughly speaking, geometrically, it sends a link L from the left-hand side on the 3 manifold N to sums of links L tilde on the covering 3 manifold, with some coefficients being long polynomial in Q. And I draw the schematic picture for the 3 manifold M. So here I have this real line. At each coordinate of the real line, you have a slice of Riemann surface. So it's really a 3D picture, but I'm not good at drawing that. So anyway. And now you could put some links into this manifold, and you could position it arbitrarily. But there are 2 special limits I would like to mention. The first special limit is if your link is sort of like an unknot, but this unknot will be wrapping some non-trivial cycles on the Riemann surface, like this little L1 here. In this case, this UVIR map gives you the so-called generating function for those BPS indices that we described at the beginning of the talk. So it counts the ground states within each superselection sector with their spin information. On the other hand, if you take your knot to be small, in the sense that it's the neighborhood of that little knot looks like R3. So namely, for example, this trivial knot L2 here. And then in this case, you run the same algorithm, you run the same computation, you get a new kind of way to compute familiar link polynomial. In this case, this 1 parameter limit or home-free polynomial. In a sense, this kind of algorithm is like a unifying picture for you to compute this ground state spectrum with spin for the stop defect system, and some new way to compute the traditional link polynomial. I think I'll skip this kind of how I construct this, but just roughly, I can talk in more detail after the talk. But roughly speaking, what one do is like uplift to 5D to look at some UN super young mills, and then this links L will physically correspond to the Wilson line in the super young mills theory. And then going to infrared just means I'm putting the theory in the background, which generically breaks UN to UN to the N. And then, of course, again, there is a semi-classical analysis where you think the Wilson lines will decompose into N abelian Wilson lines, but you also need to include corrections for massive W bosons from this UN superior Mills theory. And those W bosons have to travel according to some certain trajectories. And figure out these trajectories is a difficult part of this kind of program. So I'll just give you like really quick 2 examples of how what's the quantity that we're computing here. First example is this SU2 equals to SU2 with 4 fundamental hypertheory. So namely, I take my Riemann surface C to be a 4-puncture sphere where punctures are labeled in blue here. Then I consider a line which corresponds to a loop going around 2 of the punctures. I go to a point, and I could go to anywhere in the Coulomb branch, but if I go to specifically a particular point in the Coulomb branch, then I get a total sum of infrared lines. And most of the coefficients are 1, namely that says the ground states in those sectors are just trivial under spin, under rotation group. However, you also see this Q plus Q inverse appearing, or this 2 plus Q squared plus Q minus 2 appearing. So that means, for example, states in this sector from a 2-dimensional representation, and states in this sector from a direct sum of a 1-dimensional and 3-dimensional representation. And one could also consider a higher rank gauge series, some SU3 gauge series with some matter. And if you look at those two figures, they look very similar. So they're sort of like some cousin series. However, and I'm still looking at the line correspond to this blue loop here. However, the answer here will not be able to be fit into a page. So in total, there will be 915 infrared lines, and with all these different kinds of coefficients. So let me just summarize this part, and I will jump some of these later part also. So I've described for you this quantum UVR map for line defects in class S series. Physically, it comes from states with spin for the back defect system. And then also unify this with a new way of computing Hornfleet polynomial. And one thing, the first remark I would like to make is a little bit technical. Namely, this UVR map up here, it depends on some Coulomb branch data. So it has some wall crossing behavior. By studying this wall crossing behavior, one can extract back BPS spectrum with spin. So that's just correspond to the remark I made at the beginning of the talk. By studying the back response to insertion of the lines, you could extract information from the back spectrum. And then secondly, this UVR map I computed in a geometrical way. So it would be nice to have a more field theoretical description in this sense. And I'm sorry I'm using RG map in this sense because it's not the RG map for lines, but it's triggered by turning on Coulomb branch web in the back. Apologize for the terminology, but it would be great to have a more field theoretical description in at least some simple examples. And also, one can ask whether there's a way to construct a wall crossing invariant or generalize to a more general 3 manifold. So those are all directions one could take. And another last remark I want to make is that so a complete algorithm for higher rank series still missing. The higher rank, I mean, for example, I could do SU2, SU3, SU4, but what if you want SUN for n large? And that's a very meaningful question taking this large n limit. However, we're not able to have a complete algorithm for this large n limit. And what we have is some complicated Python code already for this lower n case. And perhaps there is a way to apply AI machine learning techniques which fit in how this algorithm works in lower rank, and they somehow miraculously could tell you what happens at large n. Now, of course, there are so many AI experts here, so I'm bluffing, but that's one possibility that I think is would be interesting to look at. And okay, so that completes the stories about line defects in classes. I think I'll just skip the line defects in class R for now, and if you're interested, I can tell you more about it. So it's more along the same line where you use some geometrical topological data to compute some observables for line defects. Except now you're thinking about line defects in a 3D series with 4 supercharges. And there is also like a related perspective from the 2D Landau-Ginzburg models. I also skip it here, but roughly speaking, if you think of the 3D series compact facts are not, you put it on a cigar times a real line. For example, cigar times real line here, and reduce on the circular direction of cigar, you get a 2D series on half space. And then it's a meaningful question to study the boundary condition at the half space. And that boundary condition is going to be correlated to what line defects you have in 3D. And in Landau-Ginzburg series, there's a complete algorithm of machinery to study this boundary condition using the series of left-shift symbols. So one can also, by doing this setup, you can translate the study of line defects to study of boundary conditions using these left-shift symbols, and that further reduces to some counting solutions to the solid time equations and instant time equations in the Landau-Ginzburg series. That's also a very interesting topic, but I'll skip it. So in the last 17 minutes, so I'll switch subject. I'll go from lines to surfaces. Before that, maybe I should ask, are there questions about lines?
Maybe a higher level question. So I guess you study these properties of these line operators, but what specific questions are you trying to answer? Are there specific theories where you think you might get some knowledge by studying?
Yeah.
these
For
line
example, there is this huge class of 4-dimensional theory with 8 supercharges where this algorithm will tell you what's the ground state spectrum for the backline defect system. And you could ask, what about non-supersymmetric theory? So one possibility is perhaps one can break SUSY in some way, and that maybe could tell you something about the line defects in non-supersymmetric theories. But I don't have anything concrete to say on that part.
Is there a general argument for like how many of these IR, like how many lines appear for like how it scales with the rank of the gauge group?
Yeah, I wish, but I don't really have argument, mostly because this algorithm for higher n is not okay. So for lower n already, it's very complicated to compute these things. I don't really have right now like an idea of, hey, you take n equals 100, what would happen?
But even with these 2 data points, it's like exponent. It's like seemed like it was hundreds. It was very large.
Yeah,
Very
but
quickly.
4 is also okay. But yeah, I don't really have a sense of how this larger would take, which is part of the reason why I mentioned the AI thing. But I would think that's still not enough data points for it to learn. But maybe there's some intermediate setup one can think of.
But also these series, they don't have some obvious legend limit, right? Because planar limit, like in Zyber-Witten series, because
I'm talking about the UV series.
There are large-end duals, but the large-end duals are not type 2 duals, not like ADS5 times 5 manifold. It's M-theory dual. So in that case, it's like ADS5 times the Riemann surface times internal S4. But there's a non-trivial fibration. It's just studied in Madison and Lewis, and then Madison also. But I guess a related question would be, is there a notion of this UV IR map in the context of that holographic?
Yeah, that's very interesting. Yeah, I should be. That should be an interpretation.
For example, I guess the Kabbalah Strasser, who talked about the geometry that corresponds to the Bloom branch of intuition pyramids or other 4D theories. Is there any understanding about how to go to the Bloom branch in
Yeah,
this theory tools?
I would think there. Perhaps there should be an interpretation, but I don't know exactly the answer right now. But there should be an interpretation. Okay, so now I'm going to talk about surface defects, and I will be brief, and because I mainly just want to talk about this exact WKB method, because it's perhaps could be taken out of the context of SUSY. But also generally, I restricted here again to this class S series, but I would like to emphasize that this kind of method potentially could get generalized to, more generic 4D equals 2 series. And I will just make a comment here, but I can talk more about it later, that you could perhaps engineer some more general Seibertine curve, which instead of just a complex 1-dimensional base, you could have higher dimensional base. Anyway, so to construct such a surface defect in 4D, I again start with a surface defect in 6D, but I orient it differently. I put it at a point on the Riemann surface and then let it extend along 2 dimensions in the space-time. So this kind of surface defect preserves half supersymmetry. And moreover, this insertion point on the Riemann surface also has intrinsic meaning as a marginal character formation parameter for the defect theory. And then again, one can go to the Coulomb branch for the back. And then what happens for the defect is it's going to develop a set of massive vacuum. And I will not talk about most of the details here, but just to say that effectively around each massive vacuum, what you have is some sort of monodromy defect or solenoid in this effective building theory. And the bottom line is this vacuum structural surface defect really encodes the Bach separating geometry. So by studying this vacuum structure of the surface defect, you would be able to recover this branch covering C tilde over C. So having made this context, recall that separating curve is some algebraic curve, and the surface defect vacuum kind of reproduces you this curve. And now you could talk about quantizing this algebraic curve using surface defect. So if we consider separating curve for some rank 1 series like SU2 bridge series with some matter, it's some algebraic curve written in this way. And I'm treating this x, for example, as momentum coordinates and z as position coordinates. And if I promote them to Heisenberg operators, I will get some sort of Schrödinger equations with p being potential. Now, of course, I'm omitting lots of important details. For example, one has to fix a quantization scheme to promote this algebraic equation to the Schrödinger equation. And from gauge theory point of view, there is a canonical way to fix this scheme, namely again by turning on this half omega background along the surface defect. But or you could derive it from some sort of like 42D correspondence called AGT correspondence. But I will not talk more about it. But the bottom line is the surface defect is useful to quantize such kind of algebraic equations into the Schrödinger equation. And because of that, the study of surface defects also helps you to understand the exact WKB method for Schrödinger equation. So let's quickly review this good old exact WKB story for Schrödinger equations.
Question.
Yes.
So when you have these surfaces, they separate regions of different value of some given order parameters. I mean, is it
There are different ways. Yeah, sorry.
linear that gets expectation values? Different, what is the physics of this?
So there are different ways you could understand this, the surface as an order defect in the sense that you have a 2D theory. You couple the 2D degree of freedom to the back 4D degree of freedom. Or equivalently, you could try to integrate out the degree of freedom on the defect, and then that's going to give you a dual description in a sense, which is disorder, namely it specifies the boundary condition of the backfields around the surface defect. But there are explicit ways to describe such surface defect. And it fits into the big general framework that I showed on the first slide with order type, disorder type.
And this surface will be characterized by some tension, which is related to.
I think
the
you're
difference
talking
in
more
the
like a domain wall
superpotential.
picture. But these surfaces are not, I mean, I'm defining it in the UV theory. I'm not thinking of it as separating some different vacuum. Or maybe I'm not understanding.
Kobe, maybe one example is like a codimension 2 twist. So the surface is something that if you go around it, in 4 dimension, you can go around it. If you go around, you pick up some of that defines this kind of surface operator.
Is a compact surface.
Yeah.
Like for
Well,
you
no.
can actually go around. They don't divide the space.
Fei is talking about the non-compact. So for example, you always extend in that direction. So that would be one particular example, but she's also talking about something more general.
Okay, so let's just quickly look at this exact WKB story. So I have this Schrödinger equation. I will make some WKB on that as follows. And then substituting this on that Schrödinger equation, I will get the so-called Riccati equation. The first step in WKB analysis is to build a formal series solution in powers of H bar. So at order H bar to the 0, you recover this classical algebraic curve, the so-called WKB curve or classical separating curve. And there are 2 branches you could choose. The bottom line is you will get 2 formal solutions to the Riccati equation. And they're just asymptotic series in H bar. In particular, those coefficients will have factorial growth with respect to the power of H bar. It's not some function in H bar. It's not an actual solution. But if you substitute these formal solutions back to the WKB on that, you get 2 formal solutions as series in H bar to the Schrödinger equation. Now, standard thing to produce an actual function is to do the so-called Brouwer summation. You take this formal solution, do the Brouwer transform, and then do the Laplace transform after that. So that's the definition of Brouwer summation. And then you get actual functions in H bar. However, a price you need to pay is that you cannot do it globally in the Z-plane. So I should say that I'm talking about the complex version of the Schrödinger equation. So the idea is like you first go to the complex plane, like the position variable will be a complex plane, and then you solve everything there, and then you could restrict to some real slice that you're interested in and get solutions there. But anyway, so in the Z-plane, you cannot do this Fourier summation everywhere. The picture looks like the following. So this is a sample example picture of the Z-plane. And I have these black one-dimensional lines carving out this whole Z-plane into different regions. Within each region, like here I label A, B, C, D, E. There are 5 regions here. Within each region, you could do Fourier summation to get actual 2 solutions to the Schrödinger equation. However, as you jump across regions, for example, jump from region D to region E separated by this black line, the solutions will jump accordingly, concretely jump corresponding to this unipotent matrix. So the bottom line is, or the big picture here is, these black lines are the so-called Stokes curves. So on the complement of the Stokes curve in these 5 regions, you get those exact solutions. They're local exact solutions. However, you also know how they jump as you go across these Stokes curve. So then you get some sort of global control of the whole thing. And how did surface defect enter the story? You could forget about surface defect or forget about SUSY. Just interpret this as a mathematical geometric trick for you to do this WKB analysis for Schrödinger equation. But if you would like to ask, how do you draw the Stokes curves? And those could be interpreted as being determined by the solid Hahn spectrum of surface defects, which I will not go into detail into that. But the bottom line is that this gives you a geometric way to solve the wave function of the Schrödinger equation and to formulate exact quantization conditions, etc. And that has a much broader application than SUSY or defects themselves.
So
Yeah.
in the Schrödinger equation viewpoint, so this P of Z, does it have to be polynomial or can be something more general?
It could be something more general, but it can be, so right now it cannot be that general. So you could get ratios of polynomial or polynomial, but for example, if you want some exponential type potential, one thing you could do is to do some change of variable to see whether there's a nicer form after you do the change of variable to recover to this rational polynomial ratio thing. But there is some limitations on what kind of potential this could be. But I want to emphasize that limitation is modulo your ability to reparameterize everything. If you can find a nice reparameterization, then that should work.
And in Seiberg-Witten story, that's polynomial. That is polynomial, right?
Yes.
So is there interpretation for non-polynomial, like some meromorphic, which
Meromorphic.
like
Meromorphic is
one
okay.
can consider like some rational functions, right?
Yes, that works.
Does it have an interpretation, this like gauge theory language? But I thought this P of Z usually polynomials, right? In the
It's your
in
polynomial.
gauge theory.
Yeah. So in gauge theory, those rational polynomial meromorphic. So that means you have some poles at positions on the Riemann surface. So in gauge theory, what happens is so your separative differential will go to infinity at those poles. It's or if you right. So I should say this in a better way, but physically correspond to where the separative differential goes to infinity. Or if you would like, there are quantities one could compute by integrating this separative differential. So that kind of quantity would also go to infinity at the puncture place.
Yeah, so maybe just to little comment. So this P of Z can have poles. I think what Fei is trying to say is that these poles correspond to the place where the Riemann surface develop punctures, where you're putting extra boundary conditions. And from the gauge theory perspective, these boundary conditions would fix, for example, some mass parameter for the flavor symmetry.
Yes, absolutely.
Except for the Schrödinger feature from the point of view of Schrödinger equation, we can actually consider general potential. It's not clear equation. It's
Yeah, yeah, we'll talk about massive like in
Like in the context of a VIM correspondence, all this stuff, basically this is selective algebraic prediction.
Yeah. So the massive case is yeah. I will get to the massive very soon. Thanks for asking some questions. So okay. So before I get to the massive, there's some quantities that's useful in this WKB business is so-called Voros symbols. So it's some say star valued actual functions on each bar, and this gamma labels one cycles of the WKB curve. You can forget about this gamma for now. But anyway, so this quantity Voros symbols say, first of all, there are exact functions in each bar. So it captures the Borel sum on WKB periods, which arrays some asymptotic series in each bar. And more precisely from the ODE point of view, you could explicitly write these Voros symbols in terms of round schemes of distinguished local solutions. And I will give an example in the next slide. So just to say now, it could be some asymptotically decaying solution as Z approaches singularity, those punctures I talked about earlier, or it could be some eigenvectors of the monogeny or along a loop. And very useful thing is this Voros symbol encodes exact quantization conditions for different spectral problems. So now let me illustrate how this works. It's a very simple modified massive operator. So this is a modified massive potential. So it's a bound Cauchy function. And this is what I was talking about earlier. So you could do a change of variable to translate this modified massive equation into the following second order differential equation with some poles at z equals 0 and also z equals infinity. And I draw this as blue dots here. Infinity I didn't show it. And in the 14 equals 2 context, this shows up as a quantum separated curve for pure SU2 supernomials. So then I would start drawing the Stokes curves in this context. So these black lines will form some closed cycles, and then I could try to formulate the following question. In the original modified massive case, I could ask, at what values of the energy do I have a bound states along the real line from x goes to minus infinity to x goes to plus infinity? And in this change of coordinates language, I would like to, the same bound states will be the bound states on the negative real axis. So I could ask at what values of the energy do I have a bound states? So essentially, when you do the WKB analysis, you get all the local solutions within each region, but two of them are special, which I call T and S here, where T is some exponentially decaying solution as it goes to 0, and S is some exponentially decaying solution as it goes to minus infinity. And essentially, this bound states requirement is to set S proportional to T, or more precisely, analytically continued portion of S. When you analytically continue S and T to some common region, they're proportional to each other. And setting this back into the Voros symbol expression, this translates to like one of the Voros symbols is equal to 1. And this Voros symbol will depend on energy in certain way. So by reversing this relation, you get the values of energies where this sort of bound states appear. So that's kind of like a generic procedure for you to study the quantization condition. And you could also consider more general boundary conditions, for example, oscillating solution and others. And one could also do some change of parameter or do some other tricks to figure out the corresponding quantization condition for such different solutions.
Are
And-
there
yes.
3/3 solutions?
So what
3/3 solutions.
Fraser means
Like it's not just a single kink, but it's like
yeah, so I think to do that one need to try harder because it's so this kind of technique is specified by this asymptotic behavior at like infinity. So to do that kind of solutions, one would need to figure out like different decompositions in terms of more fundamental solutions, but I think it's also doable. But I never tried that, so that shouldn't be optimistic, but I think one can work out the math using using the similar techniques developed. Okay. Yes.
Try to wrap up in the next
Yeah, I
few
will
minutes.
wrap it. Just so 1 minute, sorry. So one can ask whether there's a higher rank generalization. Can one do this kind of business for like higher order ODEs? And the answer is yes, but the story is much more complicated. For example, I tried to do this example, which is a particular third order ODE, and the Stokes curves becomes a mess, and you will need to analyze in total 48 local solutions. However, you could still do that, and then you could do some numerical checks regarding the Voros symbols, because the Voros symbol could be written in terms of Wronskins in some distinguished local solutions. You could do some numerical analysis solving these local solutions, substituting into the Voros symbol expression, and check it against some asymptotic series, truncated series of this asymptotic expansion. And you could say the numbers look relatively good. And there's also another way to compute the Voros symbols motivated from the gauge theory point of view by solving this kind of integral equations by iteration. So you start with some initial profile for this Voros symbol, and then recursively substituting into this equation, and then to say whether solution stabilized some number. And one can also check this kind of method against this Wronski expression of the Voros symbol. So let me summarize. I told you 3 different stories, actually 2 different stories, because the second story I skipped most of it. So those are about line defects and surface defect in SUSY field series. However, they are also related to constructions of linking variants or more practically exact WKB methods for ODEs. And in all those stories, certainly VIR maps play some important roles. And I hope I convinced you a little bit that defects are fun to study. And thank you for your attention. I apologize for going over time. And please keep staying healthy. Thank you.
Questions for Fei?
So this exact WKB, it's exact in the sense that it uses solving Schrödinger equation to like basically algebraic equation, right? So
Yes, so exact more in the sense that it's an actual function in H bar. So usually when people do like WKB approximation or something, you're doing this asymptotic series expansion, and then you say, okay, I truncate at some order of H bar, but there's always an optical theorem like which order you're truncating at. But this exact means that you produce an exact function in H bar.
for that you need to know this Voros symbol, right?
Yes, you need to know these Voros symbols, but they're also very explicit object. As I said, they could be expressed in terms of Wronskins or like a special solutions to the ODE, which I guess in most cases it's still hard to get an analytical solution, because even if you ask, okay, what's the analytical solution for this exponential decaying solution? What's the form of this actual solution? It's still hard, but it sort of like reduces to studying these kind of solutions to studying of these distinguished local solutions in a sense. And it certainly has numerical power to for various perspectives.
So did you manage to find this psi plus minus functions as an explicit function of H bar?
Yes, you can do that.
Some kind of hypergeometric function?
In special cases, yes. So there's a fun exercise, not exercise, like not homework, but you can do this kind of like a local analysis where it's the array function.
Mhm.
And you could try to do this bar summation business, and you will find out that the hypergeometric function appears as the actual solution for this array equation. And I say local just because, so I didn't tell you the details of this Stokes curves, but basically there will be this branch point. Each branch point will have like 3 Stokes curves coming out of it. But zoom in into this little region, I always get this kind of local model for the array equation in some sense. And that has, yes.
I mentioned it can be applied in situations when it's not DZ squared, but some higher order.
Yes,
operator.
yes.
What if it's some like non-local operator, some like infinite order, some differential like difference?
Difference, yes,
Mhm.
that's a very interesting question. I believe there should be a geometric way to apply to the difference case, but I don't, I'm very interested in developing that because that would be very useful, but I don't have anything to say.
Well, it's a bit complicated because one of the ingredients here is the fact that your potential makes the solution have irregular singularity. I think usually, like here it's at infinity, you have this irregular singularity, and then you have Stokes phenomenon at infinity, right?
Right.
And then when you have Stokes phenomenon, you have all these monodromy business where you can connect the various regions. But if you look at the discrete, how you define something similar in a discrete setting, it's not clear. So you need to, so if you want something identical to that, you need to understand how to have the same monodromy phenomena. So you need to understand monodromy in this sense in a discrete setting. This is actually interesting for what you say and for a lot of different things, but at least to me it's not clear.
Well, here and also here you have two solutions, and the Stokes
Yeah,
can be described as some monodromy 2x2 matrix if it's
when you go to discrete, then also again you have to specify your solutions further, which kind of class of solution you want, and there is a lot of stuff there.
Yeah, I know some work, but not along the line this separate geometry for like 5D equals 1 theories, which is relevant to the difference equation, but I don't think there is a geometric picture there yet.
But did Mourinho and collaborators consider the kind of curves that has this, not something like the correspond to this, easy square, but something more general?
I think they
In the context of the one string.
yes, in the context of topological string, they were considering curves like embedded into C star cross C star.
Yeah,
So it's like exponential.
that's right.
Yes.
That's similar.
That's exactly
Oh, that's
what
okay.
gave you the thing you want. But I don't think that's something geometric like picture
I see.
here because it's like what Stefano was saying. It's kind of hard to imagine how this kind of picture will translate into the difference equation set. But but certainly one can still use the H zero topological string techniques for some purposes.
There's a question from the.
There's a question from
Yeah.
Fei Yan, one of the students. Fei Yan,
Hi,
speak up.
Xing. Yeah. Hi.
Hi, Fei. I have a quick question about this this UV-IR map of these defects. So if I consider like a pair or several theories which are infrared dual to each other, say they are like UV different theories. So how should I expect these defects? Like there are like different defects in different theories in UV, then flow to the same infrared behavior, or it's
So first of all, the thing I talked about the infrared is just some frame theory. So but from what you were asking, I think you were asking some picture which I skipped actually. Namely, you could, for example, have some different complicated UV Lagrange descriptions which are flow to the same infrared fixed point. So in the sense that those UV theories will be separable to each other. And then of course you could ask what are the extended operators in those different UV theories, how are they going to map into each other? And I think that's an outstanding question. And in general, maybe even has in general, I don't know like a prescription for for specific series, one could study it like case by case, but I don't know a general prescription for like give a generic answer for such map between the lines.
Yeah, there's some work. For example, the Wilson lines can be mapped to vertex lines under mirror symmetry. But I don't think there's a systematic analysis. It's case by case.
Yes. But this is a very interesting thing, and not just this dual thing. I like even here I could ask something fundamental. So like this is, for example, 3D n equals 2 series, which also associated with 3 manifold. And in the infrared fixed point, those lines are labeled by links in the 3 manifold. In the UV, you have this concrete description of Wilson vertex lines. So you could ask what's the map between UV and R, not like between different UV series. And that is also only partially answered by some work by Bukov and others. Like for very simple 3 manifold. And as far as I know, it's a largely uncharted area.
I see. Thank you.
Thanks.
Okay, well, let's thank Fei again.
Thank you.
Thank you.